Let's tell you what we're going to go through today, and hopefully this will work out. It should. We're going to finish off chapter 4. We're going to do probability, and towards the end we're going to do probability trees. But we're going to look at finding the probability of two events, right? One thing followed by another, and we touched on that at the end of yesterday. And there's a whole bunch of questions doing that. And they basically, for the most part anyway, boil into two distinct groups of questions. There's questions involving throwing two dice, which is why I've got this guy again, because you don't want to have to make this up. So once you make one, keep it. And then the other is to do with picking cards from a deck of cards. And we'll be spending a fair amount of time here as some of the homework questions that involve that. Doing probability of like throwing two dice and getting a total of 7, right? Or throwing a dice and the first one's a 3 and the second one's a 2, right? That kind of question. Or what's the chances that if you take a card and then a second card that you get 2 aces? You know, that kind of question. Right? And then we'll be doing some conditional probabilities, which we have touched on, but we'll be doing ones from tables. So that'll be interesting. And then although there are only 3 of them, these are quite long and complex questions, and these are how you can use a thing called a probability tree to create or to find probabilities. And you tend to use probability trees in more complicated situations, right? When it's just 2 dice or a couple of cards, you can do it one way, but when it gets a little bit more involved, like 3 cards or other situations, you have to use this thing called a probability tree. So that's kind of the big picture. So let's do some throwing 2 dice questions to start the ball rolling. You could get a probability question like this. What's the probability that you do 2 dice, and it'll only be 2 dice, we won't do it with 10 dice or anything, right? What's the probability you get 2 dice and you get a total of 5? Now, in this table, there are 36 things that can happen when you throw 2 dice, right? Every one of these is one of the possible things that can happen. So 36 goes at the bottom. And then I just look at totals of 5. And here we go. That one adds up to 5. Second, third, there's 4 of them. 4 of them add up to 5. Simplify it down. You get 1/9. Okay. Now, you can answer all sorts of more complicated, I guess, questions like what's the probability that one of the dice, let me put in the word exactly, one of the dice is a 6. Now, if you look at the places where one of the dice is a 6, would you agree all these situations here, one of the dice is a 6? Why am I not using 6, 6 in my count? Why am I only going to count those 5 and not that last one? Now look at the way I phrased the question. Exactly one of the dice is a 6. Wouldn't that be both of them are a 6, right? So it's just semantics, but it's important. Now, would you also agree that all of these also have it? So if you're counting them, wouldn't there be 5 of these and 5 more? The answer is 10 out of 36, which simplifies a little bit into 5/18. You could do things like, what's the probability that the total is more than 8? Now, if you want to find the total is more than 8, you really need to find the total is 9, and then add the total is 10, then add the total is 11, and then you could add the total is 12. Or you could simply just do that in one go. So if you want to find out where the total are 9s, 6 and 3, 5 and 4, 4 and 5, 3 and 6. Wouldn't that add up to 9? Now, where would the 10s be? Here, here, and here. Where would the total of 11 be? A 6, 5 and a 5, 6. Where's a total of 12? So basically, if I start at the 9s, that's these 4, then add these 3, that's 7, then add these 2, that's 9, and then add that one, you get 10. The answer would be that one. And what would happen, and this one is a little bit of a trick question, the total is more than 2. How would I find the probability that you roll 2 dice and the total is more than a 2? Got this to work with. How would I do that? And I want to do it the most efficient way. Any suggestions? I want a total more than a 2.
It's easier to make 2, so you would see what makes 2 and then remove that from the 36.
Yep, which basically boils down to 35. And although we didn't mention it, didn't I use the complement to do that? That's essentially. Sometimes it's easier to find the opposite of that and then just remember to take away from one. The opposite of that is a total of 2. That's only going to happen one way. So our guy is 35, right? The other 35. And that's for this. Now we're going to do problems with 2 cards. And before we get started on those questions, I know for a lot of you this is silly because you know cards, but not everyone does. So I'm doing a quick summary again of what those look like. There are 4 suits: clubs, spades, diamonds, hearts. These 2 are black. And these 2 are red. If you had a deck of cards, you would realize that, you know, they're red or they're black symbols, right? A heart is red in color. A spade is black in color. Now, for each one of these suits, you've got an ace, a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you finish with guys that are called face cards. You have a jack, a queen, and a king. And I want you to think of the spades, the diamonds, and the hearts having the same of those. So in total, for the kind of cards that we're talking about, there are 52 cards in a deck. So far, so good, right? You probably knew that, but for those who are not as familiar, there we go. Now, I'm going to start with a 1-card question. If I said to you, what is the probability that you get a king? There are 52 cards, 4 of which are a king. Right? King of clubs, king of spades, king of diamonds, king of hearts, and that simplifies down to 1/13. Now we're going to have 2 situations. The most common one is called without replacement. And that's normal what you do. You imagine you shuffle a card, you take a card and you put it on the deck, right? And then you take the second card and you put it down. Once you put the first one down on the table, right, it doesn't go back in the deck, right? It stays there, right? That's what without replacement would look like. If you did a situation with replacement, can you imagine I had my deck of cards and I turn the first card over and it's ace of diamonds, just for argument's sake. You then pick that card up and put it back in the deck, shuffle them again, and then take a second card. Right, that's what with replacement does. There are very few, if any, games I know that you would ever do with replacement, but you know, there could be a question involving it. What's much more common is without replacement. And those are not as simple as you think. So let's figure out what's the probability that I get 2 aces, right? Without replacement. So that's going to be the probability that the first card is an ace multiplied by the probability that the second card is an ace. So the normal way to get these probabilities of 2 or more things happening with cards is you multiply the probability of each, right, event. Now, since this is without replacement, things get a little bit messy. Right, let's just worry on what's the chance that the first card I pick out of my 52 cards is an ace, and the answer is there's 4 of them. So that would be 4 out of 52. We're comfortable with the first one. Now the messy one. The first card is already an ace, right? It's happened. It's there. This is my deck of cards. I'm about to take my second card. The chances that my second card is an ace is technically a conditional probability. It's a probability that the second card is an ace, given that the first one was. Now, what does that mean? If that card is out, aren't there now only 51 cards in my deck? Also, if that card is an ace, how many aces are left in my deck to get my second ace? Are you comfortable how the two probabilities, although they're both aces, changed? The first one is different than the second. But that's very common when you do cards. Now, what you may want to do in a question like this is just multiply the top numbers together, which is 12, right? Actually, let's just do it in the calculator. I put brackets around things to be safe. 4 divided by 52 times 3 divided by 51, and get that guy, and I hope it can turn into a fraction for me, and it can. So that's 1 out of 221. So if you want to, that's quite a small number. Would you agree that's pretty small? But if you've ever played cards and somebody dealt you, like in blackjack, 2 aces, wouldn't you remember that as being a very unlikely event? That doesn't happen very often. You know, if you're in Vegas and somebody gives you 2 aces, you're going, woohoo, right? Because there's a good chance you're going to get some money if you play your cards right, as they say. Great. Now, you want to interpret that roughly. If you were dealt 221 pairs of cards, right? If somebody shuffled, turned it, gave you a card, right? Took another deck, shuffle, shuffle, 2 cards. Take another deck, shuffle, shuffle, 2 cards. If they did that to you 221 times, you know you would probably only get a pair of aces once. Does that give you a kind of impression of how unlikely it is? Right? Now, how about this one? What's the probability that you get 2 red cards? Now, there are lots of red cards, right? You could get an ace of diamonds as red, right? You could get a 4 of hearts as red, right? So would you agree that should be much bigger? So that's going to be the probability that the first card is red multiplied by the probability that the second card is also red. Right, first card's a bit easy. Out of all the 52 cards that we have, would you agree that there are 13 of these and 13 of these? So that's 26 red cards out of 52 in a deck. Does that make sense? Right. Now, imagine that's a red card. Here's my deck. To get the second probability, isn't there only going to be 51 cards in my deck now? We're trying to build up patterns here. How many of those 51 cards are going to be red? I saw somebody's lips move, and the lips moved with 25, Brandon. That's what you were saying, and you are right. And you don't want to deal with fractions, so let's the calculator do it for us. And the answer, whoops, once you convert it to a fraction, is 25 out of 102, which, if I do a quick division here, it's about 24.5%. I like percentages. So can you imagine that that's going to happen a lot, right? About a quarter of the time, right? If somebody deals you 2 cards, getting 2 red cards is like, yeah, they're 10 a penny, right? I'm going to say that a lot. So for my next probability, let's pick one of the questions from the homework. This is from question 14. And we're being asked to find the probability of an ace on the first card and a jack on the second. Right, so your first card is an ace and your second card is a jack. If you play cards games, isn't that blackjack? Which means you're going to win some money. At least that combination is. So the probability you get an ace on the first card times the probability that you get a jack on the second card. Right? Do you notice that it's first guy times second guy, right? That doesn't change. Now, there are 4 aces in a deck, so 4 out of 52 done. And I'm going to do my little visualization. There's my ace. Here's my deck of cards. Isn't there 51 cards now? How many of the 51 cards are jacks based on the fact that the first one was an ace? How many jacks do I have? 4. And if you put that combination together, you get 4 divided by 52 times 4 divided by 51, and then make it a fraction. You get 4 out of 663. And you might say, that's not very big. Well, that's correct. But that's just the probability of getting an ace and a jack. Couldn't you get an ace and a king, an ace and a queen? Right? Couldn't you get those as well? And couldn't you actually get the jack first and then the ace second? That counts as a different situation. Now, if you do all of those combinations, right, all of the different ways to get a blackjack, right, ace jack, ace queen, ace king, and you reverse it, what you get is that guy times 1, 2, 3, 4, 6. You will get that number, because there's 6 different ways to get blackjack, and that's just one of them. And I'll check this one out. See if it can be simplified. And it's equal to 8 over 221, which I'm now going to convert into, the chances that you get dealt blackjack is 3.6% of the time, right? Which is roughly what, 3, 4, let's call it 4. It's about 1 in every 27 deals. So if you were sitting on a blackjack table and you went through 27 deals, one of those would be a blackjack. Can you see how casinos make lots of money? Now, you can win other ways, right? But blackjack's the only guaranteed win, isn't it? If you get blackjack, you win. That's the rules. So these are very often, these probabilities that we're doing here are very often the bread and butter of professional gamblers, right? People who play poker for, money, or against other people to win competitions, right? Those kind of people, they know the ins and outs of what's the chances that I'm going to be dealt a certain card next, or what's the chances that my opponent has got a hand that will beat me, right? Those kinds of on-the-fly probabilities have to be kind of done if you want to be really good at gambling. Because shouldn't you only bet when the odds are in your favor, and shouldn't you probably fold if the odds are against you, right? If you're going to lose more than you win, unless you're very good at bluffing. Let's do a card one with replacement. Suppose I asked you to find the probability that you get an ace and then another ace, but the difference here is with replacement. So it's going to be the probability that the first card is an ace times the probability that the second card is an ace. Right, there are 52 cards in a deck, 4 of them are aces. No difference there. Here's the difference. I put the card down, it was an ace. It's put back into the deck, I shuffle them, and then I turn the card over. Aren't there 52 cards to pick from, and aren't there still 4 aces? Do you notice that in that context, with replacement, the probability of an ace is the same no matter if it's the first card, the second card, or even if I did 3 cards, wouldn't it still be times 42, 4 over 52? And a quick figure out what that guy looks like. And it's 1 out of 169. Which, have I got the 2 aces handy the other way? Yeah. Do you see the difference when you don't replace compared to when you do? Isn't that a little bit easier, right? Won't that happen more often? Which kind of makes sense, right? If you put the ace back in the deck, and you get more chances of getting an ace again, right? Kind of makes sense. This is with replacement. And this is without. Okay, let's go for a crazy one. I want to know the probability that I get dealt 3 kings, and now we're back with the more typical result without replacement. So that's going to be the probability of a king, then the second card is a king, then the third card is a king. Right, first time round, there are 4 kings in a deck of 52. Check. Okay, without replacement, what's the probability that the second card is also going to be a king? Right. Okay, top number.
Three.
Agreed, out of 51. Now, new third card, also going to be a king. Do you notice there's a pattern here? Won't the bottom number now be 50 cards? And how many kings are left if you've already done this and that? Only 2. Now, getting 3 kings. Can you imagine you're playing poker, right? And you get dealt 3 kings. Aren't you going to be thinking, I'm getting a new card today, right? That's a hand that's probably going to win, right? More than, almost 3 aces, I guess, will beat you, right? But it's very rare. I wonder how rare. So it's 4 52s times 3 51s times 2 50s. Now, this number might be too big for the calculator, and that's fine. If it is, the answer is going to be a decimal, which is that guy. And then we're going to see if I can turn it into a fraction. If we're lucky, it'll work. No, okay. So now we have to interpret this weird number. I'm just going to call it 1.8 e to the negative 4, right? When numbers get really big or really small on a calculator, they go into a thing called scientific notation, which I hope you've met in something like, say, chemistry, right? So this means 1.8 times 10 to the negative 4. That E is just the calculator's way of saying 10 to the negative 4. Now, if you know what that is, that's great. But if you're not sure and you want to see what that looks like as a decimal, the negative 4 means you start with 4 zeros, including this 0. And then you do 1/8. Can you see how small that is? Right. That is your answer as a decimal. If you want your answer as a percentage, so you are probably going to see 3 kings dealt to you roughly 1 in every 50, where 1 in every 50,000 hands. Can you see why, if you get 3 kings, you should be pretty comfortable that you're probably going to win that? And the whole trick in poker, not just in, it's not the game I play, but the whole strategy in poker is, if you know you've got a winning hand, aren't you going to try and sucker the other guys into betting against you? Right? You don't go in poker and go, yay! Because won't everybody fold and you'll get nothing, right? Don't you go, okay, I'll try. You know, you'll try and give this impression that it's not that good, I would suspect. But wow, tiny. Are we comfortable about cards? If I said, what's the probability of getting 2 red cards, or 2 aces, or a king and an ace? Are you comfortable about calculating their probabilities, especially without replacement, which is what you typically would expect? Are we good? Right, okay. I'm hoping to see that. That kind of takes us through a bunch of questions in it we've kind of covered. Try to find my list. Here we go. So we've basically done those two. Right, so let's move on to conditional probabilities. So conditional probability is the probability of something happening when you're given an extra piece of information, right? So it would be things like, what's the probability that you get a king given it was a face card, right? Or what's the probability that it's an ace given that it was a club, right? Or what's the probability it's a club given it was a card bigger than 10, right? There's a given part, a thing that you're told is true. So the one that we're going to do is a little bit more complex than the stories I just gave you. So based on data from a statistical abstract, only about 15% of seniors get the flu. So I'm going to write that down. 15% of seniors, S I've written down, get the flu. Okay. However, about 22% of the people are under 65 get the flu. So 22% of people who are under 25 get the flu. Okay, so I'm assuming seniors mean you're over than 25. So the world only has 2 groups of people, the old fogies and the young'uns. And 15% of old fogies get the flu, and 22% of young people get a flu. And then it goes and says, another piece of information, in general, there are 14% senior citizens. So what you've told me here is that 14% of the population are seniors, and that must mean the other 86% of the population are young. Okay. And then it goes on and asks us these questions here. So I've got a little issue with Windows. Oh, anything in here I should do? Oh, that is interesting. Aidan, if you look at the chat, has said that if you do the alpha y equals enter, you get what's called a stacked fraction. And that always does the answer for you. So have a play about with that. That's cool. Right, now there is a lot of information in here, and we are going to use it to calculate some probabilities. So the first question was, what's the probability that a person selected in at random will be a senior? So, well, that's this number here. So that's 14%, but as a decimal, 0.14. Question B, what's the probability that a person selected in random from the general is under 65? Well, the probability that they're under, I'm just calling them young, it's less writing, is 0.86. How do I know that number? Because in the story, they only told me the 14% bit. How do I know that that's 86%?
It's the complement.
Yeah, it's a complement, exactly. So we'll move on to question C now. We haven't actually done any examples of conditional yet, but they come eventually. I'm trying to find that question because I scrolled out the way. It's up here. Why can't I find things when I need them? Just hang in there for a minute. I've lost my page. Now, what's the probability that you get, let's read it. What's the probability a person selected at random from the general population is under 65 who will get the flu this year? So it's what's the probability that they get the flu given that they're young? Well, what's the probability that you get the flu given that you're young? Okay. I'm going to create a probability tree to help me do this. Actually, I can do that. There are two ways to do that. Which way am I going? Well, I could do it that way. I'm just thinking of another way of doing it. I'm going to call it the probability of A given B. And that is the probability of A and B divided by the probability of B. Can you remember that formula? We did it yesterday. I'm going to use that one. I was going to use the tree diagram, but I don't need to. This is going to work just fine. So what's the probability then that you get the flu and you're young? So that's the A and B bit. Well, somewhere in this list they told me what's the probability that you get the flu and you're young, and the answer is 22%. And then the other one was, what's the probability of B? The probability of B is, try that again, probability of being young, and we know that as 0.01. So we should be able to put those together and get the probability of A given B is 0.22 over 0.86. And that's whatever that comes to. 0.22 divided by 0.86. Hopefully I got that the right way around. And if I didn't, I just have to switch places and I'll get the answer. I think I read it the right way. Right, next question we're going to do is from a table, which is actually the more common version of this. So, and actually it's a lot easier as well. Here we have a table where they've got a whole load of information, and they've also, I'm glad they've done, oh, don't want the answers. Go away answers. Just a distraction. Right, let's go back and forward a couple of times. Then I spend forever trying to find where I was. There we go. I think it's there. Right. This is a version of question 19. Your numbers will be a little bit different. In a sales effectiveness seminar, a group of sales representatives try two approaches to selling stuff to customers. So you're going to sell them a new car, right? So they're saying, which one is more effective? So $580 people, and the ones that were aggressive, they got 271 sales and 309 didn't buy anything, right? So if you ever been to a used car lot and the guys, I call them vultures, you know, they circle around you and then they're zooming in and how much money can you afford, and no, this is a blah blah, right? The guys that are pushing it and are doing a heavy job, that would, I think, would count as aggressive. And if you can see here, 271 out of 580 would be a measure of how successful that is. Now, if you look at the second group, also 580, can you see that you've got a much different distribution? Now, just looking at the raw data, and to me the raw data is just basically those two rows. Just looking at it, wouldn't it look like passive salesmen actually sell more cars? So if I asked you what's the chances, an aggressive salesman would only be doing 271 8580, and I'll do that calculation right now. 271 sales out of 580, and that's about a 47% success rate. And those that are passive, well, that would be 461 also out of 580, and that's about 79%. Not quite, but you know, almost twice as successful, right? So if you were new to the job, people would say to you, no, if you want to sell a lot of cars, don't be in the customer's face. Don't try and sell them something they don't want, because most of the time people just get turned off by that and they walk away. So just be there when they have a question, let them come to you. Don't push the car, whatever it is, you get more sales. I must be honest, I've not bought that many cars in my life, but almost without exception, I seem to always get the aggressive one. When you've went for a car, do you tend to get people who just, you know, they're almost like in your face trying to, you know, sell you something? And okay, let's calculate some probabilities. So they've put letters to abbreviate things. So this one is, what's the probability that there's a sale by any method out there? Well, total number of sales was 732 out of a potential customer base of 1160. And I thought I was typing things in. 732 sales out of 1160. And they want the answer as a fraction, so that might simplify. So I'm about to see if it does. Pretty sure it does a little bit at least. And 183,290. So there we go. Now, what's the probability that you get a sale given that you did the aggressive one? Right, now since you did the aggressive one, isn't all your data going to come from that top row? And that would be the 271.8580 that I did a few minutes ago. And you can simplify that if it does. Now, if you do the passive one, that is the 461 sales. So this time, all your numbers are going to come from the middle row. You get 461 divided by 580. And again, you can simplify it. Now, it says, are the events getting a sale and the passive approach independent? And I'm going to have to leave this for a second because it involves us remembering something. So here we go. There was a test for independence and it went something like this. If the probability of A given B was the same thing as the probability of A, then A and B are independent. Can you remember that? Right. The probability of A given B, if it's the same number as the probability of A. Okay. Now, the probability that you sell a car, given that you use the passive approach, was 461 out of 580. The probability that you sell a car was I'm going to have to move this a minute because I can't see it all, was 183 out of 290. Would you agree that they are not equal? And can you trust me, even if you simplify them, which I doubt you could, they're still not equal. So that means, right, that they're not independent. And what not independent means is that one has the effect on the other. And that's kind of obvious. Would you agree that being passive had a better effect on sales than being aggressive? Right? Let's be silly. Imagine they had salesmen and one of them wore black suits and the other one wore grey suits. But apart from that, they sold the cars the same way, right? They weren't aggressive or passive, right? They just did the same thing, right? Would you agree that probably the colour of your suit has very little, if zero effect on how many cars you're going to sell, right? Grey suit, black suit, nobody cares, right? Green eyes, brown eyes, nobody cares. Those would come out as independent. In other words, these two probabilities would be the same number. Now, the next question that they have in that card one looks something like this. What's the probability of A, that's the aggressive approach, and S, and the other one is probability of the passive approach and S. So we're trying to find the probability of both those events occurring. And I'm using those formulas to calculate them. So the probability that you have an aggressive and you got a sale, that combination, is the probability of A given S times the probability S. And I get that from the tables, although you can't see the tables anymore. Given that you got a sale, right? Given that you got a sale, the aggressive people, there were 271 of them out of the 732 sales, times the probability that there was a sale. We've already calculated that, and that's 183 out of 290. So you multiply them together, you've got your answer. Now for this one, the probability that passive aggressive, given that you have a sale, well, there was 461 of them, 8732, times the sale, which is 183, 8290. And that big ugly thing is your answer. Now, what does N stand for? Oh, they then went on and they did questions involving no sales, and you could do that. Moving on. Next question is for the medical people. And it's how do you analyze tests, right? So you go into the hospital, you'll probably get tested for various things, right? Yeah. And you might just get tested for COVID, right? That's a test that could happen, right? But tests are not infallible. You know, tests are wrong sometimes. And so what we're looking at here, are you looking at question 20? Is that what you're saying? Okay. Here is some data to do with a test. Let's pretend I know it's a COVID test, right? Somebody's got a COVID test and this is the results. You can test positive, which means the test says you've got the disease, right? You've got COVID. Or you could test negative, in which case the test says you don't have COVID. Now, when it says condition present, that means the truth, right? That person did have COVID, right? And when it says the condition is absent, that's also the truth, right? That means the person didn't have COVID. So when you look at this table, and the columns and the rows are helpful, but the four numbers right now that really matter, right, are those four guys there, right? There are things called false positives and false negatives. Pick Brandon. False positive, what does that really mean?
It means that you might not have the condition, but it shows that you have the condition on the test.
Right, so you test for COVID and it says you've got it, but you didn't have it, right? That's it, right? What's a negative one then, Liana? If you get a negative rather than a false positive, you get a false negative. Liana, can you hear me? No. False negative. What does it mean?
It means that you had it, but it said you didn't have it.
Aren't both those bad things?
Describe that.
Yeah. Aren't both those conditions bad, right?
Yeah.
For different reasons. Now, let's move off COVID and pick a more serious one. Let's pretend it was a test for HIV, right?
Okay.
Now, if you get a false positive, the doctor says, oh, the test results will come in and they say you've got HIV, but you don't actually have it. Mm-hmm. Now, that's bad psychologically. That would freak you out, right? And you all sorts of bad things happen. But at the end of the day, you won't die of a false positive.
Agreed.
Right. In fact, if your doctor's anything, won't you do other tests just to make sure?
Yeah.
Now, if you get a false negative, that's much more serious, isn't it? Because what that says is, oh, your test comes in, you don't have HIV, but you really do have it. Now, can you see the damage that that mistake would have, right? So if you're manufacturing a test for COVID or for HIV or for monkeypox or whatever the next one is going to be, right? If you're doing a test for that, wouldn't you prefer to have one of those mistakes to be as small as possible, even if that made the other mistake a little bit bigger? So wouldn't you much prefer to have very small false negatives? So we have a whole load of data here. Let's find out what these probabilities are, and you can calculate them by using the information that's in this. So what's the probability that you test positive given the condition is present, right? So you're positive and the condition is present, right? So what's that? That's 105 out of 130. So the answer to that one would be 105 divided by 130. And if I could hit the buttons, I would get that. Do they tell you what they want? Oh, they want fractions. Okay, that'll do. Now, when that number there, I'm turning into percentages because my brain doesn't like weird fractions. So 105 out of 130, that's about 81%. Just easier in my brain, right? 81%. Okay. Now, what about a false negative? Oh, so by the way, isn't that them getting it right, essentially? Right, you have HIV and they tell you you've got HIV. Right, a false negative, right? Well, given the condition was present, so we're talking about here, and negative, that's 15, right? So you tested negative and the condition was present, and that is 15 out of 70. 15 out of 70. And let's see what that looks like. That's about 21%. Oh, that is horrible. Would you agree if you took a test and 21% of the people, right, tested as being okay when they really had whatever the disease is you were testing for? Would you agree that is a ridiculously large number? In fact, if you were the FDA, shouldn't you pull that test as not reliable? In fact, weren't some of the early COVID tests pulled because they were very unreliable? Right. So whatever that magic number is. Now, you know, for some tests, you might let something slide, right? It's better than having no test at all, right? But, you know, if it's something really important, you probably should, you know, I would want that number to be less than 1%, in my opinion. And the smaller, the better. Now, what's the probability that it's negative given the conditions absent? Well, condition is absent. There's 55 of them. And what's the probability then? You get the condition absent. You got, well, I should be able to just do that one there, isn't it? The other 79%. Right. Now, if you wanted to do a probability like the probability, so I'm talking about question F here, that the condition is present and it's a negative on the result, right? So that's me writing that down now. I'm going to have to use a formula for that one. I can getting dizzy here, closing windows all over the place. Okay. If you think of condition present as A and testing negative as B, this is really you being asked to find A and B. And isn't that the probability of getting of A given B times the probability of B, right? We're using that formula again. Are we good? And, oh, can you see this? No. Okay. Can you see it now? Right. So we're being asked to find what's the probability that you get the condition is present and they tested negative, right? So that's an A and B. And I'm just calling them A and B right now. So we've got the general formula. So what that is going to become then is condition present and negative. So it's going to be the probability that the condition is present given that you tested negative times the probability that you test negative. And each of these probabilities I can get, if I can get back to my question, right, here we go, I can get from that table. Right, so the probability that the condition is present given that you tested negative is 55 out of 70. There are 55 out of a total of 70 in that group. And the probability that you test negative was 70 people out of a total of 200. And so you put that package together and I'm running out of time here. Can you just multiply it and get your answer? Are we cool with that? Right. So that was a conditional probability question involving tests plus and minus. And the one that we just did, oh, my screens went wonky on me again, was question, because it's gone forever. Yeah, that was question 20 that we were just doing. Question 21 is the same kind of thing, right? Same, different numbers, but basically the same kind of question. Now we're moving on to, we're almost finished this section. I think I'm going to have to return to the table. I've got the answers here, but I'm not going to rub them out because I just want to get a move on with this fella. Right. Here we have a whole set of table, but basically the country America has been split into the East, the Midwest, the South and the West. And are customers more loyal in the East or in the West? I don't know. The following table is based on information from a recent survey, and the columns represent the length of customers' loyalty in years at a primary supermarket, and the rows represent the regions. Okay, so for instance, in the East, there's 460 people they got information on. And out of those 460, for instance, 135 of them had been going to the same grocery store, right, for 15 years or more, right? So that's like, yeah, well, I've been here for about 20 years in Bremerton, and I still use Safeway a lot. It's just me. So, you know, I'd be one of those people, right? Some of you might not be as loyal, right? You might, you know, don't go to their store, right? You go to someone else's store. And on the other hand, if you looked at the West, there's 382 people that they got data on, and 41 of them were less than 1 year. So that particular store wasn't their typical go-to one. Now, here are the probabilities. Let's see where they come from. What is the probability that a customer chosen at random has the following characteristic? So the first one has been loyal for 10 to 14 years. Right, now if you go 10 to 14 years, can you see that's that 291 out of everybody? Can you see where those two numbers are coming from? If I asked you, is the West given, so I better should put what is the probability then that a customer chosen at random, okay, is from the West, given that he or she has been loyal for less than a year? So let's see where these numbers came from. You are told that they're from the West. So if you look at the West, can you see that there are 382 of those people? And I've lost the question number.
It was E.
There we are. 382 of them, right? And if that group then, oh darn, this is not working for my brain. I've lost which question I was just answering.
You were doing question E.
Okay,
Okay.
so what's the probability that they're from the West, given that I've been loyal for less than a year? Right, if they've been loyal for less than a year, it's 157 in the bottom, isn't it? And how many of them were from the West is 41, right? Can you see the 41, 157? Right, now if you switched it round and said, what's the probability then that they have been less than 1 year, given that they're from the West? Then since you know they're from the West, you're using that row. So 382 in the bottom and 41 in the top. You see the difference? 41, 83, 82. And the one that we just answered was this column. So it's 41 out of 157. If you're told that they're less than a year, you're using the column. If you're told they're from the West, aren't you going to use the data from a row? So it's all about making sure you're using the correct row or the correct column, depending on that question. So let's pick that one. You're told that they're from the South, that he or she has been loyal for less than a year. So you're told they're from the South, and what's the chance that it was less than a year? So since you know they're from the South, the data comes from here. So that should be what, 53? That's the less than a year, out of 682. Did I read that the wrong way around again? I did, didn't I? You're told that they're less than a year, so it's the 157, and you're trying to find that they're south, that's 53. I think it's the fact that this bit is missing that's making me read it back to front. I think it would have made my life easier if they just gave me the whole sentence every time. Let's pick one from here. If I tell you that the person has been loyal for 15 years or more, what's the chances that they came from the East? So if I tell you that they've been loyal 15 years or more, it's this column. And what's the probability that they come from the East? That would be 135, 86, 18. Okay. Now let's turn the story on its head. Suppose I told you that they were from the East. What's the probability that they would be 15 years or more? That would be 135, 85, 60. So you see that 135 stays the same, but is it out of 460 or is it out of 618? Doesn't it depend on which one they told us is already known, right? If you tell me I'm from the South, I know to use the row that's south. If you tell me I've been loyal for 15 years or more, it's a column, and then the other number you get from there. God, I made that harder than it should be. Okay, we are now moving on to the last piece of the puzzle. And I'm going to do that with notes. We are going to make probability trees, and they're quite useful, and they could have been used in some of the earlier questions. So I'm going to tell you some information about a place called Lichfield College of Nursing. Have you heard of that? Any of the people in the medical thing? Is Lichfield College of Nursing like a biggie? People know about it? Right. So some of you know about it, some of you don't. Evidently, at this nursing college, 84% of the incoming people are female. And the rest are male. And so 86% needs to be written as a decimal. So if they tell you 3/4 are female, right, it's much better just to turn it into a decimal, right? You can get away with fractions, but it's just easier because you're going to do a whole load of multiplications on your calculator, and so decimals work better. But never use 86 or 14, right? If it's a percent, always turn it into a decimal. Now, if I read a little bit further, records indicate that 70% of the female students graduate. Now, 70% is that. How many fail to graduate? They don't tell me that, but I know what it is. How many fail to graduate? That's all you need to know. 70% graduate. It's not a trick question. How many fail?
30.
There. Isn't it the complement? The rest. Now, what about the males? Well, a certain percentage of them graduate, and obviously the rest fail. And in this one, 90% of the males graduate. And won't that make 10% of the females graduate? What we've done in this diagram is represent all that information that when you go back and you get that question, it's a whole big long sentence, right? 80% are female, and of the females, 70% graduate, and so on, right? But that is the finished tree. Now, from that tree, you can calculate quite a lot of questions. For instance, so I would like to know, what's the probability that a student graduates? I don't care if they're male or female. And you can get it because one of the things you should do on one of these probability trees is that you should find the final probability. Right. 86 female, 70 graduate. You multiply those two together. So 0.86 times 0.7, and that's 0.602. That number at the end represents the percentage of people who are females who graduate. So 60.2% of Litchfield College will be female graduates, right, at the end of the, whatever it is, 3-4 years. Now, if you go the other one, it's 0.86 times 0.3, because one thing followed by the other you typically multiply, and that comes out as 2.58. So what's that? 25.8% of students who went to that college are females who failed to graduate. Now, if you do the males, there's 0.14 times 0.9, and the answer to that is 0.126. And if you do the last one, 0.14 times 0.10, you get 0.014. These are called the final probabilities. So each one of these probabilities represents one combination. For instance, males who fail, of the total population, right, of everybody who went to that college, right, that went in on the first year, 1.4% of them are males who failed. 12%, 12.6 are males who graduated. 25.8% females who failed, and 60.2% males who graduate. Now, once you've got that, you can then answer this question. What's the probability that you graduate? Which ones of these four represent students who graduated? Well, doesn't that represent a group of students? That's females who graduated. And doesn't that represent males who've graduated? So if you want to find how many, the percentage total graduation is the females who graduated plus the males who graduated, and that's 0.728. So at this particular nursing college, wouldn't their success rate be pretty close to 73%? Does that seem accurate. I don't know if you know. I don't know. You know, is it roughly 70+% graduate in the nursing programs? Is it more, less? Yeah, around that value, right? Now, I can also find the probability that you fail to graduate. And I could do it two ways. Couldn't I add this and this? And that would get me the answer. And I can also tell you the answer is that. How did I do that without adding the two failures together? I used that. How did I use that to figure out this?
It's the complement of it.
Yeah, complement, if you want to go that way. And you see, you can do, you know, whatever you like, right? From this table, we agree it's possible now to find those things. I could even tell you what's the probability that you're a female and you graduate. Actually, isn't it just that number up there? Female and graduate, you see. That would be female and you failed. This would be a male and you graduated. And this would be a male and you failed. Do you like tree diagrams? They're a bit of work to create, but aren't they very helpful when you want to answer questions? Nothing to do with this, well, nothing to do with probability, but I'm a nosy person. Would it be reasonable that the proportion of males to females is like 86% of the nursing is females and 14% are males? Does that seem a bit in the high side here, or does that seem, yeah, it's like 1 in 10, 1 in 15 in my experience. Anybody want to chuck in that one? Brandon?
That's
Your
fairly
opinion.
reasonable for the industry.
Is that typical in your situation, Liana? Right. So here's the next killer of a question. Why? Why is there not a lot of males going into nursing?
There's been a lot more males recently that I've
Good.
noticed. Yeah.
But, well, okay, then why in the past?
I think it was because it was mainly a female thought out profession, just like business was usually a male dominated profession. It's just kind of the status quo, what it was. It kind of has always
So
been.
it's just social norms.
Yeah. And like, I mean, they're changing now. So it's probably why.
Cool. That's good to know. Yeah, because if you think about how many nursery, I call them nursery, kindergarten, whatever Americans call them, you know, the tiny little babies, the little tots. There are very few males who go into that job, aren't there?
Yes, that is true.
And that's not changing so much. So certain social ones are changing and others maybe
Yeah.
not so much.
So like that they group that with labor and delivery. There's not really a lot of male labor and delivery nurses, but you'll see a lot of male nurses in like other specialties. So like,
So within the nursing professions, it's not equal. Some are more than others. Oh, interesting. I think that society just does that to people, don't they? They put you into little boxes, and I don't like boxes. I think you should be whatever you want to be.
Agreed.
Right? Although, after saying that, I'm now going to contradict myself. I do not like women boxing. I don't think women should box. I just think there's something about it that just freaks me out, and I don't like it. So I am sexist as well, but in general, I think women should do anything that they want. Let's move on. Let's do another tree diagram. There are only 3 of them, so it shouldn't take us too long. The next tree diagram is draw a T. Draw a T. I can't say that word. Tree. Tree. Spit it out, Donald. Draw a T diagram to display all the possible head tail sequences that can occur when you do 3 coins. Now, thankfully, you don't need to write all those probabilities. You know, these decimal 0.5s all over the place. They only want the shape, and they're doing it vertically. So here goes. Would you agree you could get a head or a tail? That's it. Right, you throw a coin there. Then you could get a head and a tail, a head and a tail, and then you could get a head and a tail, head and a tail, head and a tail, head and a tail, right? So I'll put some head and tails to finish with. And one of your pictures will look just like that. Now, they ask you as question B then, thankfully not too much. How many sequences have exactly, oh, that's a cool word, exactly, 2 heads? And now that I've done that, I've realized I'm going to have to put a head here, tail here, a head here, finally a tail here. Now, out of all 8 guys at the bottom, only some of them are exactly 2 heads. For instance, see this one right at the end? Wouldn't that be a head, head, and a head? Wouldn't that be 3 heads? What about this one next to it? Would that be 2 heads and a tail? Right, so I'll put a little asterisk to remember that one. What about this one here? Well, it would be a head, a tail, and a head. Yep, that one works. Agreed? Right, next one, this one here. That would be a tail, a head, and a tail. That's no good. What about this one? A tail, a head, and a head. That one works. Nothing, 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 right? So it looks to me like there's just 3 of them. You agree? Out of those 8, there's 3. If I then went on and said, what's the probability that you get exactly 2 heads? Wouldn't the answer be 3 out of 8 possibilities? And so you could do, I could tell you what's the probability you get 3 heads. Wouldn't it be 1 out of 8? Because that can only happen once. And so on. Now, the last one in the list is going to be the ugliest one. So you have 8, what you got? 8 balls in a bag. And 3 are red, 4 is blue, and 1 is yellow. Right, so this is going to be the ugliest table in the world, and I'm going to have to put probabilities in, and I'm going to use fractions. So you are going to pick 3 balls out of this bag. So this is essentially a version of equation 25. So let's start with the first ball. That first ball could be one of 3 colors: red, blue, or yellow. Agreed? Now, since there's 8 of them, 3 out of 8 red, 4 out of 8 blue, 1 out of 8 yellow. So far, so good, right? That's me taking 1 ball out of the bag. Oh God, I just noticed something that's really good. You're only taking 2 balls out of the bag. It's much smaller than I thought it was going to be. So that's the first ball. Now, the red one, you could get a red, you could get a blue, or you could get a yellow. And then you could get a red, you could get a blue, or you could get a yellow. And lastly, you could get a red or a blue. Why does that last one not have a yellow choice?
Because there's only 1 yellow
And it's already
used.
it's already used. So each one of these little branches, that's what we call them, we now have to calculate the probabilities. And you got to remember, like the card, right? You've used up a card. That's a red. The chances that the next one is going to be a red, well, there's only 7 balls in the bag, and would you agree there's only 2 of them red? Because you've already used up a red. Does that make sense? 7 balls in the bag, 2 are red. Why 2? Because there used to be 3, but you used 1 up. Now, you've used a red up. There's still 4 blues out of 7. There's still 1 yellow out of 7. So do you see the combinations that add up? Right, this one's a blue. That means you've got 3 out of 7 for red. You've used up a blue, so there are now only 3 out of 7. And there's 1 yellow, 1 out of 7. And then you've got the yellow has happened. So that's going to be 3 out of 7 for the red and 4 out of 7 for the blue. And then if you get the last guys, right, the guys at the end, right, the final probabilities. For each one of these destinations here, right, each one of these, we're going to calculate the probability. So you multiply these 2 together and you'll get 6 out of 56. If you multiply these 2 together, you get 12 out of 56. If you multiply these guys together, you get 3 out of 56. Then you get 4 and that's 12 out of 56. That middle one is also 12 out of 56. And that end one is 4 out of 56. This one is going to be 3 out of 56. And this one at the end is going to be 4 out of 56. If I added up all of these horrible fractions, what should the total be if everything is done correctly? Right, so if I added all of these up, what should I get? Now, don't add them up. In theory, what should I get?
56.
Yeah, 56. Does it make sense it should add up to 1? Right, 56 out of 56. And if you had time, that's how you would check it. Right, so let's ask some questions using this probability tree. So what's the probability, for instance, that I get a red and then another red? Well, if you do a red and another red, isn't it that's 6 out of 56? What's the probability that the second one is red? Now, it's a little bit different, right? So the second one is red is that guy, agreed? Isn't it also that guy? And isn't it also that guy? Isn't there 3 different ways that the second ball that came out was a red one, right? 3 different ways. So that one, this one, and lastly that one. And what's that? 18, that's 21 out of 56. Now, if I didn't have a tree diagram, would you agree that question would be almost impossible to figure out? I mean, I'm not even sure how you would start without that diagram. Are you comfortable with that? Yeah. And I have perfect timing, I would think.